Hello. In this video, we are going to talk about an experiment on a linear capacitance meter. Linear capacitance meter. In this circuit of this experiment, we will use an IC which is called IC 555 timer. So before we begin discussing about the capacitance meter, we will spend some time on understanding this particular timer, this IC 555 timer. What it does, it can be used to generate square waves like this. It can be used for other purposes as well, but also it can generate square wave with a desired frequency and also with a desired duty cycle. So you can control this time, this is the time period, so you can control this time or the frequency, you can control this time or this time as well. Okay, so let us see what is there inside an IC 555 timer. It is very simple. It has two op-amps acting as two comparators. So these are two op-amps. And there is a potential divider which is three resistances connected in series like this. So this is a potential divider. One side is at, say, potential V. It can be the supply voltage. You can connect this to, say, for example, 10-12 volt supply. The other side is grounded, so this is at potential 0. And these three resistances are equal. Call them R, R and R. Therefore, the potential at this point will be 2/3 of the entire potential. So this will be 2V by 3, and here at this point it will be V by 3, 1/3 of the entire potential. Okay, now we will definitely have two input terminals for each of the op-amps, and the purpose of these op-amps is to compare a voltage. Okay, say at here, I'll draw it later. Say there is a voltage here. These two op-amps compare this voltage, whether this is greater than this 2/3 of V or less than 1/3 of V. So for that, this op-amp will compare whether this voltage is greater than 2/3 of V. Therefore, I will connect this reference, this 2/3 reference point to the minus terminal, and from here I will connect it like this. So therefore, the output of this op-amp will be 1, or logical 1, or in other words, it will be positive when this voltage is greater than 2/3 of V. Okay, so call this as P1 maybe. So this here, the output will be logical 1, that means positive or equal to the positive supply voltage of this op amp, say plus VCC minus VCC. That means it will be equal to plus VCC when V1 greater than 2/3 of V. This op amp I want to use to check or compare whether this V1 is less than 1/3 of V. So how do I connect it? I will connect say this to this and this to this. So whenever this voltage V1 falls below 1/3 of V, the output will be 1. So output here will be 1 when V1 is less than V by 3. Okay, good, great. Now where is this V1 coming from? Okay, so this V1 is connected to a capacitor like this. So let this be a capacitor C, which gets charged and discharged periodically. So let me ground one terminal of this capacitor, and through the other terminal this capacitor can get charged or discharged. Okay, so let me connect a few resistances, and then this side positive, some voltage, and a set of resistances through which this capacitance is connected. So then when I apply this voltage V, then this capacitor will be charged, and therefore this point will have a increasing potential as current comes in through this set of resistances. This potential will increase, and at some point what will happen, so this potential increases, so this point increases, the minus is always at the same value. So after a while when I connect this value will go up, so this value will go up. Okay, and if I by chance say discharge this capacitor, maybe by removing this, I connect this side to the ground, or maybe I just connect somehow say this to ground, then the capacitor voltage will be going down, and therefore this value will be going down, and then after a while this op amp output will be positive. Now this two I will use to drive a flip-flop, which is an RS flip-flop. I can connect it in different ways. Maybe I do it this way. So now what will happen, so it will have an output, maybe call it Q. It can also have a complement Q bar. So Q will be 1. So Q will be 1 when this set is triggered. Okay, when this set is triggered, then Q will go up. Now when this set will be triggered, when this op amp output is 1, which means when this capacitor is charged at a voltage greater than 2/3 of V. So when this V1, we can also call this VC, because this is capacitor voltage, maybe that's more meaningful, so let me call it VC. So this is also VC, this is also VC. So this voltage I can call, then I can say that Q will be 1 when S is triggered, which means when VC goes above 2V by 3, and this will be equal to 0 when VC falls below, if I by some means discharge this capacitor, and then if VC falls below V by 3, then this reset will be triggered. If this voltage goes down, then this output will be 1, this reset will be triggered, and the Q will be 0. But also if VC VC lies between this 2/3 of V greater than VC and V by 3, if VC lies between these two values, then Q will not change. Why? Because if VC is between these two values, then this output is also logical 0, this output is also logical 0, and set reset both being 0, the output stays unaltered in a SR flip-flop or RS flip-flop. So then the output will remain same. Now what I will do, there is one thing missing. So I have a path for this capacitor to get charged. I also need some means for this capacitor to be discharged. Okay, a path for the capacitor to be discharged, otherwise this voltage will not change. So I'll give a path maybe like this. I need a switch. And then I will take connection from here. I'll connect it to a switch, which is basically a transistor. Okay, so this is a transistor, which is a switch, and this end is again grounded. So what will happen if I turn this switch on? Okay, if I turn this switch on, then the capacitor will discharge through this path. Then the capacitor will discharge like this. This is the discharge path and this is the charging path. If this switch is off, then this is not there, then the capacitor will be charged through these two resistances. If this switch is on, then the capacitor will get discharged through this transistor. Now this transistor is a switch, so I can connect it this way. So what I want this switch to be on as soon as the capacitor is charged enough. What I mean by enough? As soon as the capacitor is charged above this 2/3 voltage, okay, then this will be 1, right? So I will do this. I will just connect this point like this. So now you see the circuit. As soon as the capacitor gets charged above 2/3 of V, this is 1, so output becomes 1. This 1 comes to the base of this transistor. Yeah, you may, this is not a precise circuit, you may need some biasing resistance, bases, etc. But okay, it's a logical switch. So this part is not precise. I'm not bothered about it right now. This is not our concern. This is just a logical switch. So this Q will turn this on and the current will flow like this. The capacitor will get discharged, and as soon as this capacitor is discharging and its value goes below 1/3 of V, then this will be on. This will reset. Okay, this will reset this SR flip-flop. Output will be 0, so that means this switch is off. Then the capacitor will again start charging. So this is how, what happens, this capacitor is periodically charging and discharging, and synchronously this Q and Q bar, they are also oscillating between 0 and 1 and 0 and 1 periodically. So if I plot maybe this VC as a function of time, if this is time axis, then the capacitor voltage increases. Okay, it tries to go to the value V, but before it goes to value V, say if this is V, if this height is V, when it is at 2/3 of V, so this is 2/3 of V, this Q will be 1, so this will turn on this switch and the capacitor will start to discharge. So then the capacitor starts to discharge, it will try to go to 0 potential, but before it goes to 0 potential, at this point when this is V/3, this op-amp will come into action and this will reset this flip-flop, switch will be off, therefore the capacitor will again start charging. So it will start going up towards V, but before it reaches there at 2/3, it will start coming down. This is what happens for VC. So this is VC. Now if I also plot time versus this, so that I can plot as, definitely I know that when this capacitor is discharging, that means this switch is on, which is only possible if this Q is 1. So this Q will be 1 here. Okay, Q is 1 when this is discharging, and this when it is charging, then the Q is when it is charging, this is off, so Q is 0. So Q is 0. So this is logical 1, this is logical 0, and it oscillates like this. So this is Q, and definitely if this is Q, then Q bar you can plot also. If you want to consider this voltage, it will just be negative of that. So that will be like this. Sorry, yeah, this will be like this, this way. Or maybe I start my discussion from this point. So it's not there, so you see the 0, 1 and 0, and this will continue. Okay, so this is how IC555 timer can be used to get square waves. Now, okay, here the timer comes as a chip, an integrated chip with a number of pins, and so most of these things, op-amps, this potential divider, this switch, are actually inside this timer 555. So it's like maybe this part, and most of it. So this from here, even this line is inside. So okay, forget this red line. So okay, this is the internal diagram of the IC555 timer, and we have access to a few okay, let me use a different color. This red is nothing. So this resistance, this capacitance, okay, these are outside the chip. These you connect through the pins, they are outside the chip. This, obviously this voltage supplies, this should be also accessible from outside as a chip. The grounding point should be accessible as a chip. Okay, now I won't go into the pinout diagram, that which pin is which pin, because this is given in your manual. Let me just show you briefly the manual. So basically this RA, RB are these two resistances, this capacitance is this capacitance. Okay, so these are outside the chip, you connect them through this terminals. You can give this supply VCC, you can connect this, there is a ground terminal, so these things are there. And I leave to you to figure out how the relation between this diagram and this internal diagram. Let me just do a small math to find out this on and off time, on and off, or 1 and time for this 1 and 0 levels. Okay, so how long will this capacitor take to get charged from V by 3 to 2V by 3? This time. This is the time when this Q is 0 and Q bar is 1. So let's find out this time. Okay, charging time. Okay, so I'll not do detailed derivation of this, this voltage Vc as a function of time, which by solving a differential equation. I assume that you can do it yourself, or you have already done it in some previous courses. I will just directly write what the expression of this part will be. So this is being charged from a value of V by 3 towards a value of V. So Vc will be, if I start my time from this point, will be it starts from V by 3 and then it goes to this height. Okay, so then I need 2V by 3. This is where the capacitor tries to go. This is the starting point, starting value, and this is the target increment. Okay, this is how far the capacitor wants to go. The capacitor wants to go to a value of voltage V. So this is the increment targeted by the capacitor, and this will happen exponentially. This will not be happen at once. So initially I will have 1 minus e to the power something like this, t by some time constant. Okay, so that at t equal to 0, this 1 minus 1 is 0, this is not there, but at t equal to infinity, this part is 0, this will be achieved. Okay, so this is how the form should look like. And how should the tau be? Tau, we know it's the resistance times the capacitance of the charging or discharging path, and this is being charged. It's charged through these two resistances. Okay, so call them RA and RB. So the charging time constant will be total resistance RA plus RB multiplied by C. So this will be RA plus RB whole multiplied by C. Okay, R times C, where R is the sum of RA plus RB. Or let me also write this tau charging time constant is RA plus RB times C. I am rewriting this because this part is looking ugly. Okay, so this is how it will charge. Now the question is, how long will it take to reach this level of 2V by 3? Okay, when this goes to 2V by 3, that means this part should be half. Okay, this part this should be half. Because if it is half, then half times this will be V by 3 plus V by 3 will be 2 by 3. So this should be half when the charging is complete. When charging finishes. Okay, so this should be half, which means 1 minus this thing is half, so this itself should be half. So which implies I am running out of space. Okay, so if this is, if I start my time from here and this time is, call it T1, charging time from 0 to T1, then at T1 this should be half, so which means e to the power this thing minus T1 whole divided by RA plus RB C e to the power, this entire thing should be half, which will mean that e to the power, I just remove the minus sign, e to the power T1 by RA plus RB T1 whole divided by this, then this should be equal to 2. Okay, because I'm getting rid of this minus sign, so this 2 goes up, so which means T1 by RA plus RB times C, this should be log 2 ln 2, and ln 2, the value of ln 2 is the value of ln 2 as per my calculator, it comes out to be 0.693. So this will imply T1 is equal to 0.693 RA plus RB times C. Okay, I'm really sorry for this I'm running out of space. So this is T1, this is the time required for this capacitor to get charged from V by 3 to 2V by 3. Okay, cool. Okay, let me now compute the discharge time. Okay, so the capacitor is discharged from 2V by 3. It's trying to go to a value of 0. Okay, so Vc will be of the form, so it starts from 2V by 3 and it's decaying exponentially, so it will be e to the power minus t by the time constant, and now the time constant will be the resistance of the discharge path. Okay, the capacitor is discharged through RB only, RA is not there, it is discharged through RB. If I assume this transistor to have no resistance, then this will be RB times C is the time constant for discharging. Okay, and then if I assume that time from here to here, okay, is T2, so this time is T2, then at T2, not at T2, I mean starting from here after T2, okay, so then this will be e to the power minus T2 by RBC. Okay, so for, I might have already noted that for this computation I'm assigning this point as my time origin and starting my computation of time from here. It makes it slightly simpler. Okay, so this should be equal to V by 3. Okay, it should get discharged to V by 3. So then I can find the value of T2 from this. How? Okay, so at T2 this is equal to this. Okay, so at T2 this is equal to this, which means, okay, I can get rid of this V, get rid of this 3, which means that this thing e to the power minus T2 by RBC is equal to half. So then that will again means that e to the power T2 by RBC equal to 2, which will mean T2 by RBC equal to ln2, which is 0.693 approximately, and therefore T2 will be RBC multiplied by 0.693. Sorry, C like this. Okay, so by controlling RB, I can control the time for this on period, and by controlling maybe this RA and RB together, because T1, if I look at this expression, T1 was RA plus RB multiplied by C into 0.693. So I can control the off time as well. So this is how IC 555 timer works. Now in the later part of this video, we will talk about a linear capacitance meter which will use this IC 555 timer. So now let's have the circuit for the capacitance meter. Okay, and here is the idea. Before I draw the circuit, the idea is this. We know that the charge that a capacitor can hold, Q, is equal to CV. Now therefore, if I apply a constant voltage, fixed voltage, so V is fixed, then the amount of charge a capacitor will hold, that depends on the capacitance value of that capacitor, and they are linearly related, proportional to each other. So more this capacitance is, more will be the charge held by the capacitor. So what I will do, I will take a capacitor, okay, and I will charge it. I will charge it up to a voltage V, fixed value. Okay, so I will do this test with a fixed value of voltage always. I'll never vary V. Okay, let the other end be grounded. So the capacitor gets charged up to a value of voltage V, which means it will have Q equal to CV, and then I will disconnect it. So for example, I will disconnect it or switch it off, and then I will connect it to a discharge circuit, okay, which will have a meter on the path, an ammeter, and through the ammeter I will let the capacitor discharge. Now what I will do, once this capacitor is discharged, I will again connect the capacitor to this V so that it gets charged again, and while it's being charged I will disconnect this discharge path. Let me redraw it in a better way, like this. So I have this capacitor, and I have, say, a battery with voltage V. Okay, this is grounded. This is a double through single pole switch, and from here I say have a meter, ammeter. This side is grounded. This jockey I can connect either to the voltage source or to the ammeter. Okay, and I will move this jockey, call this K, and it call these two positions, call it P1, position 1, and position 2. I will operate this key K at a regular fixed frequency, regular interval. I will connect it first to P1, then to P2, then again to P1, and then to P2, like this. So this key K, this key goes between P1 and P2. Call this as P1, call this point as P2. Then this, if this is time, then at a regular interval I am switching the, this is a schematic to convey the idea that I am moving this switch to the left to P1, then after a while to P2, P1, P2, P1, P2, and so on. Okay, continuously. So when K key at P1, then the capacitor C is charged with Q equal to CV, and then K, when K is at P2, the capacitor is discharged, C is discharged, and it discharges the amount of charge which is equal to CV. This entire charge will go to the ground through this meter. So the meter, so the charge that will flow through the meter, charge flowing through meter will definitely be this Q, which is equal to CV, and once again I will get it charged and then discharged through the meter. Now if I am operating the switch at a frequency, say F, if frequency of switching is equal to F, right, that means every second F times I have this capacitor charged and F times this capacitor discharged. So then every second the current or the charge that flows through meter every second is equal to, in total, F times Q. Every time it discharges Q amount of charge, and I charge and discharge this capacitor F times every second. So this will be the total amount of charge that discharges through this meter. So the average current of or through the meter is equal to this F times Q. So this is the average amount of charge that passes every second through the meter. Of course, this is not happening at uniform rate. This is happening, sometimes there is some flow of current, and then no flow, then again some flow, then no flow. I'm not very sure about the exact pattern, whether it's square or anything, but there is a fluctuating current. Sorry. So this is time axis. So there is a fluctuating current that goes through the ammeter, and the average value of that is F times Q. Now if this ammeter is sensitive to the average value, and if this frequency is very high, then the meter reading will be FQ. Of course, if this frequency is very small, then the pointer will oscillate, so it will go to some value and then again come down to 0, some value come down to 0 if this frequency is small. But if it is happening so fast, then the pointer cannot move so fast, then it will stay at an average value, which is equal to this F and Q. And now F and Q will be FCV, because Q is equal to CV. So the reading of the meter is equal to FCV. Now V is the voltage to which I charge the capacitor. This I keep as constant, fixed. This F I keep as constant for all the tests I do. Every time I do this test, I use the same value of V, same value of F, so I can keep them constant. It is in my control. I keep them as constant, and therefore the reading of the meter reading is just proportional to C, because these two are constant. So the meter reading is linearly related to the capacitance of the capacitor. So this way we can have a capacitance meter whose output will be linearly related to the value of the capacitance. So this is kind of the philosophy of the circuit that we are going to look at in more detail. So this is the idea or philosophy. Charge a capacitor and discharge it, charge and discharge it. The average current will be proportional to the capacitance. Okay, now let us look at more detailed circuit. Okay, so what I will have is this. But before that, maybe I just tell you that this scheme can also have a few different varieties with the same underlying philosophy. So one possible scheme could be, maybe I have this ammeter here. Instead of having it here, I can have the ammeter here. So it's like this. I have an ammeter. This is the voltage to which I charged the capacitor, and this is the capacitor. This is the single pole double throw switch, and this is the discharge path, short circuit path. Fine, no problem. Okay, so the capacitor will be charged through the ammeter, and the amount of charge it will collect will again be Q equal to CV, but that comes through this, and it will discharge through this. And then if this switching frequency is F, then the charge that the capacitor collects per second is Q multiplied by F, that goes through the ammeter, and that is the average current will again be F times Q. That will be the average current. average current F times Q, which is equal to F times V times C. So this is also a small modification of the previous scheme, where just I have the ammeter here instead of having it here. Same, right? I mean, whatever charge flows here, same charge flows here. So I can have the ammeter here as well. So that means I can have several similar modifications. And so let us just see one circuit that we will be using in the lab, and which is like this. So I will have this capacitor, okay, and then okay, so then this one end of this capacitor is connected to the meter, and the other end here I give a square wave. This is from, you might have guessed it correctly, this is from 555 timer, IC 555 timer, which you have talked before, configured as an astable multivibrator, which generates this square wave, and this is connected here. Okay, so this comes here on this side of the capacitor. So now what will happen? Let this be the 0 level. Okay, 0, and this is the high level. This is VCC, positive. So what happens? I periodically apply plus and 0 voltage here. Now when I apply plus voltage, the capacitor should get charged, with this side being plus and this side being relatively minus, and when this is positive, okay, when this is positive here, then this side will get charged to plus, this side will get charged with positive charge, this side will have negative charge, and this flow of charge will be through the meter. Okay, and in fact, not so important, but you may even think a bit more deeply that when this is plus positive, I mean this point is at positive value. So I mean, from, if this is a parallel plate capacitor, if you think in that way, then from this plate electrons will be attracted to this, and then this plate will become positive, which in turn will attract electrons from the ground. Okay, so electrons will come like this, which in other words means the current flows, positive charge or current flows like this to the ground. This is not the focus how exactly charge flows, but what you should focus on the fact that when this is plus, okay, then this, to have my KVL balanced, I need same positive voltage to be developed, to be generated across this capacitor. Therefore this capacitor must get charged, this side with positive charge, this side with negative charge. So which means current will flow like this and then like this through the meter. Okay, so when this is positive, current must flow like this, plus to 0. Very simply speaking, when this point is positive, current will flow like this, from plus to 0. So basically current will flow from here to here, and then from here to here. Okay, here to here, and then from here to here. Okay, great. Okay, now this is what happens when this is positive. Then after that, if I make it 0, okay, so this, now if I make it 0, let me redraw without any harm. So now it is charged, it is already charged. Okay, it is already charged with this side having plus q positive charge, this side having minus q. Now this goes to, this point goes to 0 volt. Okay, if this goes to 0 volt, but this is already charged, so then this charge must get away. Okay, because otherwise KVL is not balanced. I mean, this is at 0 volt, this is at 0 volt always. How can I have this potential difference of V here? So this must immediately discharge. So the current will now flow in this direction from here to here, which means from here to here. So current flows from here to this plate, right side plate, and from left side plate to the to whatever is connected there, whatever source is connected there. So this is discharging, this is charging. Okay, now, and this happens periodically because I'm applying this square wave here. So this periodically goes to positive, then the capacitor is charged, then it goes to 0 volt, then the capacitor is discharged. And then in one cycle or one half cycle, the current is flowing from top to bottom here, and and here bottom to top. So net current on an average will be 0 through the meter. Okay, so we cannot measure how much charge was accumulated in the capacitor and how much is discharged, because it will the average of charge and discharge current will always be 0. So what we will do, we will play a trick. We will here give a path, say through a diode. This is a one-way path, so the current can only go like this. So the diode is only useful for the capacitor to be charged, to be discharged. So if the capacitor wants to discharge, which is shown here, so note that during discharging, okay, let me for more clarity, let me draw it separately. During charging in this capacitor, current flows like this. This is the current. Okay, and during discharging, current flows like this. Okay, be careful. This is how. Let me highlight this part. So this capacitor, I'm zooming it here. This is how it is charged. This is how it is discharged. Now, this diode allows the capacitor to be discharged through it. Current can go like this. Okay, but from here, like this, but it cannot go like this. So now, during discharging, current can flow like this, or like this, or together. So discharge happens through both of them. Charging happens through the meter only, because charging cannot happen through the diode. Okay, so here discharge allowed, here now charging and discharging both allowed. So discharging and charging allowed. So through this, right now both discharging and charging allowed, only discharging allowed, but through this only both discharging and charging is allowed. Now what I will do, I'll put a high resistance, high enough resistance here, and therefore during discharging this is a easier path. This is a high resistance, high enough resistance. So during discharging, when current is supposed to go from the ground to here, this is an easier path. So almost all the current will flow through this, no current will flow through this. So during discharging, now this meter will not be used. But during charging, current cannot go through this. So this is the only way current has to go to the ground. So charging will happen through the meter, discharging will happen through the diode. So by now we have understood the circuit that we are going to use in our experiment. So this video I will end now with some discussions which you also may discuss in your report, which are quite interesting. Okay. So number one, the current that flows through the meter, is it constant? It's not. This current flows only during the charging. During discharge, current flows only through this. So the current through the meter here is not constant, but I don't know its exact shape, but I know that okay, during discharge there is no current, only during charging there is some current. I don't know, I don't bother much right now about the exact shape. You may think deeper. That's okay, that would be really interesting, but at least I'm sure that it's going to be oscillating through the meter, and this may even cause the pointer to oscillate if the frequency is not very high compared to the dynamic, compared to depending on the dynamics of this pointer, this pointer may even oscillate. So we will use a small remedy, trick, a small filter. Okay, so we need a filter. A filter is needed. What kind of a filter? Okay, let us redraw this. Let us redraw this. Okay, so here is the circuit. Let me draw once again. This is the capacitor. Then I have a diode through which the capacitor gets discharged, and then another path. So here I have this meter through which the capacitor, this is the unknown capacitor, call it C, X for unknown. Here I give the square wave input. Here is the meter. This is the high resistance, not very high, I didn't mean that very high, higher to the definitely higher than this diode, so that charging so that discharging is not occurred through the meter. Okay, so this is our resistance, this is the circuit, and here I know the current will be like this. What I will do now, here look at this part, maybe from here to here. So this part, after this resistance, I will give a shunt, something like a shunt, basically a parallel thing, which is this. Okay, So, and here I will have some resistance. If the meter resistance is not enough, I can put some more resistance, call it R2, extra resistance. If it, I'm telling you why. So now what happens here at this point, the current at this point is like this, oscillating. Okay, so through this current goes only during charging and no current during discharging. But here, so that means here the current will also be oscillating, but capacitors are low resistant to high frequency oscillations than resistance. So therefore this current, which is AC, the oscillating part will go through this. Most of the oscillating part will go through the capacitor, and the low frequency parts, if you do a harmonic analysis of this current, low frequency part will go through this. So only the low frequency part will go through the meter, and average value DC, pure DC, that will go through the meter only. So pure DC will go through the meter. Okay, because pure DC can never go through capacitors. This is open circuit to pure DC. So here definitely at this point, so at this point the current that goes from here to here is definitely oscillating, because I need current here only during charging. So which means this part should also have oscillating current, but this filter or this bypass path is so set, this arrangement will allow the higher frequency components to go through the capacitor, and the DC plus some low frequency things will go through this meter. So the pointer will not oscillate. Now if you wish, you can actually spend time on finding out what should be the value of these capacitors, this filtered capacitance, these resistances, etc., so that the desired pointer behavior is achieved. You can really spend time on that, and that will be really nice and great. That's how engineers design their meters, etc. It's not easy. There are so many intricate details that we do not talk in class, but they're there. So what should be the value of this capacitance? What should be the value of this resistance? How much should be this resistance? You may spend time on that. If you can come up with some solutions, put that on the report. That will be excellent. That will be really, really great. But we are not talking much about that in this video. In fact, I do not know much details about that. Okay, so that's point number one. Then point number two, important point to be mentioned, is that what will happen if I want to measure very high, or say very high Cx with this scheme? What can happen? The problem that we may face is that now Cx being very high, so then it needs more charge to get this, during charging, to have this voltage difference of V, if this is V, and 0 if that is so. So for this capacitor to get charged up to voltage V, it needs more charge and more time, and then it may happen that it doesn't get enough time to get charged to full voltage of V. So then the charge Q that flows during this this on time is actually less than Cx times V, because it it's not getting enough time for going to the full voltage. So in that case, Q will be lower, and then the meter current IM, which is QF, that will also be less than CXVF. So the meter reading will no longer be linear with the capacitor, with the capacitance value. So at high capacitance value, this scheme may not be usable. Another point you may observe, but then you can also have a solution that you may increase the time period of this square wave, have say lower frequency square wave. Then okay, the capacitor gets more time and the linear behavior will be restored. So that's another point you may consider thinking. Finally, you can come up with alternative circuits. Think if you can come up with alternative circuits, maybe with the same underlying philosophy as we have seen that okay, we have two schemes, like putting the meter here or here, then the next scheme that we finally have used is this, where I mean there is no switch, there is no real switch like this which alters between charging and discharging, but this diode and this resistance actually makes it possible to have a distinguished path, different path, two different paths for charging and discharging. So think if you can come up with some more alternative schemes, some more different arrangements of the diodes, meters, different placements, that will also be nice. That means that will stronger your understanding. It will help in clearing your concepts. So think more, enjoy more, and when you are bored, relax.